Okay, so the dimensions, this is one of those dimensions, or a basic one of those dimensions. So that's the product. So we had the fact table in the middle. The dimension table stores information about each dimension. So in this case, the product key, here's the product key. Remember, it was FK, it was a foreign key in the fact table. It's a primary key here in the product dimension table. So there's one row for each product in here. And the fields are things like the product description, the brand description, category description, department, packaging type, weight, dietary description, all the attributes that go with a product. Okay, so each row in the sample, in the product table will be a description of a product with all these fields describing the attributes of that product. And what we end up with this is the start of our star schema. We have our fact table in the middle. The primary key of the fact table is the day, because we're recording sales per product per day. And then these each link to the dimension table. So here's the product key, links to our product dimension table. Our store key links to a similar set of attributes about store attributes. And you can see here, these have not been defined yet, these various attributes here. Okay, warehouse design. Okay, so this is Ralph Kimball, Data Warehouse Toolkit. This is the design process that he outlines very briefly in the book about if you're designing a warehouse, how you go about it. 4 stages: select the business processes to model, declare the grain, choose the dimensions, identify the facts. So the first stage is basically your scoping exercise. What is the scope of the digital warehouse, of the data warehouse? Is it going to cover the entire organization? Often not good to do because it's too complicated. Start with a small one department or something like that, and then move up and expand the system to other systems. So basically, it's deciding which business processes to model on the basis of business requirements and available data. Simple as that. Basically, scoping out what you're going to do. He then suggests that you identify or declare the grain of the data warehouse. Now, the grain of the database warehouse is the lowest scale at which the facts are stored in the data warehouse. So the grain of that table that we've just seen is temporally 1 day, because that's the lowest resolution that we're storing the information at. We could have had a grain of an hour, and then we'd have summed everything sold within each hour. But we've decided to aggregate to the day, so at the temporal domain, the grain is 1 day in this case. General principle that the facts should be made available at the lowest level possible, which in the sales system should be individual sales. That's the sort of overarching principle, but the reality of it is that we may aggregate to some kind of higher level. So we may also aggregate to different levels of granularities, such as the product level, store level, region level. One of the reasons why facts were aggregated in early data warehouses is simply data volumes. Storing all that amount of individual records 20, 30 years ago was very hard. It's now possible. So to a certain extent, some of these emphases change through time. The lower the grain, the greater the exploratory potential. Basically, if we pre-decide we're going to aggregate data to a certain scale, if somebody then turns around and says, well, actually, I'd like to know exactly what happened in this situation, down to the individual data items, you can't actually provide that if you've already aggregated. Choose the dimensions. So the grain of the facts table defines the primary dimensions of the model. Things like, for that facts table, we had time, we had store, and we had product. Okay. But we can add additional information, additional dimensions to the facts. Say, for example, there might be a promotion dimension, where sales are identified according to what promotions they were sold under and things like that. Importantly, facts must have just a single value in each dimension. Think of this as a multi-dimensional scatter plot. That's the way I kind of think about it. To locate a point in a two-dimensional graph, you can only have one value for that point. Otherwise, you have to draw 2 points. So every fact must just have a single value in each dimension. And if you find that adding these secondary dimensions creates a situation where you have more than one value in a dimension for each fact, then you have to go back, reconsider your grain, reconsider your dimensions. I must say, I find separating dimensions from grain quite difficult in my head. I read it about 5 or 6 times yesterday. I still felt that I would do this in one, consider the grain and the dimensions in one step, but his methodology separates them two. Okay, so once we've gone through this, we've got this is now changed to an individual transaction. So this is the examples out of this book, out of the Kimball book. And he starts off with an aggregated data warehouse, and then he changes it into an individual sales warehouse a few pages later. So in this case, we're talking about individual products. We've got a date, whether something was sold, what was sold, which store was sold. Now we've got our promotion dimension for which promotion it was sold under. We've also got the transaction number, which is presumably some kind of till number or something like that. And then there's various information that we may more data that we may need to link to these sales. For example, how much was actually spent. So we now need to expand that facts table out. We need to find out which facts appear in the fact table. We've had this where all possible, they should be additive numbers that can be summed across all dimensions. Some values, just to point out, can't be summed across all dimensions, and they're all either called semi-additive or non-additive. Let's not worry about that. Okay, so we add in some additional facts here. So the sales quantity, so how many of so this is not, I don't know what the POS transaction number is, so I think we are looking at groups of things. We're still looking at groups of things, sorry. So we're looking at sales quantity, how many dollars, I don't know, these are financial things that I have no idea about, but they're some kind of financial figures. So we start adding these additional fact attributes onto the fact table. Basically, each record row in the fact table is one set of measurements on our. The date dimension, here's an actual example of the date. This is an example of the date table. Here's the, so we have one row for each day, okay? 1st of January, 2nd of January, 3rd of January. Then we have fields that describe that day in terms of other temporal ways of measuring time. So for example, we have the date. Each day is a day in the week. So Monday, Tuesday, Wednesday, Thursday. So we now, whenever we have a transaction fact, a set of facts, we take the foreign date key, look up the value in the primary key, and immediately we know it's a Tuesday because that's been pre-calculated and is available in the data table. So there's no function that turns that date and works it out. It's a Tuesday. That's already been pre-populated into the data. That means querying is quicker. Similarly, we've got the calendar month, the year, the fiscal year, all the various things, weekday, weekend, that a business person might want to know. He doesn't want to have to write a spatial function to return the day of the week. He just wants to be able to click on a field that says, show me this by day of the week, and it automatically displays it, the data by day of the week, rather than month of the year, or whatever other variable he wants. So these are different ways of looking at the date pre-stored in a table, lookup table basically. Here's the example of the product key. Each layer, so each product has a description, a category, department, fact, content, that kind of information. So all the descriptors for the various products are in one table. When we're interested in a particular sale, we look up the product key looks up the row in the table, instantly we get an answer. So that's our data warehouse. But one of the problems with the data warehouse, it could be huge, gigabytes, terabytes, things, words that I don't know, yettabytes, that's another bigger one. Okay, so we've got a problem of data size, which means these queries can be really slow, despite the fact that we've optimized our database for maximum speed. What can we do? One approach is to build what's called an OLAP data cube, which is a data structure that stores multidimensional data in a hierarchical views onto multidimensional data. Right. So the data where it says stores the data at the lowest level in a star schema. The schema is optimized for query, but may be slow. We need a data model that supports responsive exploratory analysis at scales relevant to the problem domain. Answer, OLAP data cube. The data model that generalizes multidimensional data to a discrete data cube. We'll see concept hierarchies. It supports concept hierarchies defined on dimensions that can be explored at different scales. And the data is already summarized to these different scales, so it's really quick to analyze. Now, that's all very well, but what does that actually mean? First of all, conceptual hierarchies. This is the idea that you look at the world and you can divide things into a hierarchical structure. Here's a simple geographic one. We can, with different levels, we can look at the whole world. We can split the world into continents. We can split the continents into countries. We can split the countries into regions. We can split the regions into cities or sub-areas. This is a discrete spatial hierarchy. So we could provide access to our manager. He can say, I want to see the data split by the world. I want to see the data split by continent. I want to see the data split by country. I want to see the data only for Europe split by country. And basically they can choose which scale they want the data to be aggregated to. So that's a discrete categories, but we can also do this with continuous values by just producing these sort of range bands. I want to see all the values. I want to see only the values 0 to 499. I want to see them 0 to 999. So the user is presented with these categories rather than being able to state, I want to say 250 to 350. So these hierarchies are defined on all the dimensions, or the dimensions at least that you want to define them on. So here's a number of different dimensions with a number of different conceptual hierarchy, each with its own conceptual hierarchy. So we've got time. So for time, we could look at it by year, by quarter, by month, or by day. Okay, this is a hierarchy of time. If we look at products, we could individual products. We've got subcategories and full categories. God knows what that is, but basically baked goods, bread and rolls, panini, something like that. We've got individual customers in a city, customers in a region. So we've got these different hierarchies for each dimension. Right. A user would want to query among one to all of the dimensions in your star-based schema at one of the hierarchical conceptual levels in each of those dimensions. That means there are 16, if we have 4 data sets, 4 dimensions, there are 16 combinations of dimensions over which a user may want to query the data cube. Each combination of direct dimensions we call a cuboid. So our 4-dimensional data set has 16 potential cuboids in it. We have this apex cuboid, which is all 4 dimensions. Somebody wants to query on all 4 dimensions. There is also one-dimensional cuboids where they just want to query on 1 dimension. 2D cuboids where all the combinations of two dimensions are. 3D cubes where all the combinations of 3 dimensions. And then at the bottom, we have the base. I must say, I don't quite see what the difference between all and 0 is. I think that's 0. That has no dimensions in it. And this is all dimensions. Anyway, so you've got 16 combinations of dimensions. 16 combinations of dimensions. So your data model needs to store averages or counts or whatever statistics you're interested in for whatever attributes you want for all 16 combinations of cuboids at each hierarchical level for each dimension. And it basically calculates all those figures and stores it in this hierarchically structured multidimensional cube, which I'm not even going to, it hurts my brain to think about this, but it's that's what it does, and it's all stored in a single data model. Then the users want to explore these data cubes. Now, how you explore these data cubes is, so this is the sort of conceptual way you explore them, as opposed to the software. You don't actually see your software. You don't really see a 3D cube, and you don't you may do these operations through any kind of interface that may create a graph, a time series graph, a scatter plot, a map, or anything like that. Think of these as the SQL-like operations that you can do on your multidimensional data cube, rather than how you actually physically interact, the user physically interacts with the data cube. So for example, you can do things, these are really quick operations, so you can slice your data cube. So here's a 3D data cube. A slice just returns a single value. So in this case, we've got dimensions to do with North, Southern, Middle Europe. We've got various types of categories of camping accessories. We've got the years of sales. Once we've got our data organized, here's the data values in this cuboid. This is a simple cuboid without any hierarchy shown. So slicing, we just take 1 values, and it's the equivalent of doing a sort of SQL query where sales, where year equals 2004. So that extracts this set of data, which can be displayed in some form to the user. So it's a very simple operations to extract these data, extract subsets out of this data. Dicing is just doing the same thing on 2 or more dimensions. So here we're removing some of the subcategories, and we're just showing, we diced the cube. It's basically 2 slices in the same dimension in this case, so we can analyze a reduced set of data. We can roll or drill up and down these conceptual hierarchies. So here, outdoor, my German is so appalling, I have no chance of knowing what that means, but so outdoor something or other. But anyway, that's your category. You can burrow into that layer, and then you get the subcategories, information on data on the subcategories of the outdoor, whatever it is. Some kind of shoes, outdoor shoes, right. There's also a pivot function that rotates. Now the user doesn't see a 3D cube on their screen and fiddles around with that, although that is possible. This is mostly, think of this as the operations that can be done on a hyperdimensional data cube that extracts values that you can then present to the user in an informative fashion. So apart from seeing that regional hierarchy of geography, we haven't mentioned space at all. And to be honest, the whole idea of data warehousing and GIS, they kind of different histories. They don't intersect a great deal. But people are making efforts to use it in different areas. And this is one example, 2008, where a spatial data warehouse for exploration and environmental research. I put the paper up online and read it in your own time, but just to give you the real headline sort of story is that in this case their measurements were stream temperature and other measurements of water quality. The dimensions were things like month, obviously, time, land use, because land use implements the characteristics of the water, and also things like what watersheds, rivers and things form a hierarchical watershed, so it allows you to burrow into watersheds. This is their database schema that they came up with for their warehouse. Here's your stream survey data, your fact table, things like fish species counts at each location, stuff like that. Then we have the various dimensions, the river reach, the biological site, the different scales of three different scales of watersheds, information about the watersheds. Note that the spatial information is hived off in these spatial tables, which just store the spatial information. I'm not sure why they hived them off into these individual further tables. They could have been integrated into here, possibly. I don't know. Then they created an interface, because I've said these data cubes and things, they're not interfaces, they're a data structure. So how do you interface with them? Well, they developed an interface in ArcGIS Server for a map-based interface onto these data. So basically, here's the fact table dimension on the left-hand side, and you can decide what fact you're going to show on your map. Facts or facts. You then can select the dimension information to use in the visualization. And finally, you've got a key showing the various things. These are all black and white, which is rather horrible, but everything. So we've got the key. So this is the initial interface as it comes up. Then the user, we've got a conceptual hierarchy defined on the basis of the watersheds. So 12-digit watersheds are small water management areas. They're embedded hierarchically within 8-digit watersheds, which are hierarchically within 6-digit watersheds. Think of it just like an administrative hierarchy, basically. So basically the function of zooming in on the spatial dimension, if you zoom in on the map, you're moving to a different conceptual scale, geographic conceptual scale, and the interface automatically changes to show the appropriate conceptual scale in the watershed dimension. So in this case, what they're doing is they're summing the number of sites. I think it was a bit unclear, I thought, what exactly they were doing. The shading of the watersheds, this is the 8-digit watersheds, indicates the variation with or the diversity of particular species within that watershed aggregated from individual sample sites. So we can zoom in to spatially drill down from the 8 to from the 6-digit watershed. So the 6-digit ones are the largest ones. They contain the 8 digits. So we zoom in. As we zoom in, we drill down to the 8-digit watersheds. Then we can drill down further to the 6-digit watersheds, and eventually the individual sample sites that have been aggregated to these different scaled spatial units. And then when you go right down to the most detailed level, the monitoring site level, you can see the individual sites, and they're displayed over a Google backdrop. And we also get graphs appearing that show, in this case, the number of each of these taxa species that were sampled at each of these individual locations. Just to summarize, okay, so warehouses are cleaned read-only extractions from operational databases, which are also combined with various external data, and are often structured in a star-based schema. These star-based schema may be directly interrogated with data mining tools, or that data may be then summarized into these multidimensional multi-scale OLAP data cubes which allow rapid and meaningful data exploration, but only through some kind of interface onto that data cube. So the data mining techniques themselves are delivered through interfaces that are designed to facilitate exploration, discovery, and patterning that data set. I can't say I find that a very satisfactory example. If anybody else comes up with a better example of spatial data warehousing, I'll be interested to see it, because I wasn't very... It seemed like it was just adaptive scaling. It seems like you could do exactly the same through a bit of adaptive scaling in ArcGIS and some other things, but that's often the case. You can do the same thing in many different ways. Okay, any questions on